Hello students, so continuing our lectures on quantum mechanics for nanomaterials. I will put it in this way, type it. Quantum mechanics for nano materials. Previously, in our previous lecture, we have discussed about the concept of the wave function, the phase velocity, and the group velocity, the wave particle duality, and also to some extent the constructive interference and the condition for the constructive interference, that is d sine theta is equal to n lambda, and we use this constructive interference concept in the case of X-rays, where the total path length is equal to n lambda, and it is known as the Bragg's law. Now, in this lecture, we will proceed further. As introduced in our previous lecture, the Schrodinger's equation, which in the most simplest way is written in this form: H Hamiltonian operator acting on a wave function is equal to E in energy operator acting on the wave function. Now, the correct wave function must reflect the de Broglie relation, that is lambda is equal to h by p. This should be reflected, and E is equal to h cross omega and p is equal to h cross k. So these are all get reflected in the Schrodinger's equation when we write it in its original form. Now, the solution also must be compatible with the Davison and the Germer experiment. So that is how we have h cross square k square by 2m into v psi is equal to E psi. So all these things are getting reflected in these Schrodinger's equations. That is why it is considered to be the most acceptable form of equation representing the flow of or mechanics of the wave function. Now, based upon this Schrodinger's equation, there are certain boundary conditions. First boundary condition is that this Schrodinger's equation, this should be continuous. Second, it should have a continuous derivative. And the next is psi x should be a single valued, and smooth. Single valued and smooth, as the probability of finding the particle is psi x square. Now, based upon these three boundary conditions, we can let us have few examples where which is not acceptable for psi x. For example, if psi x is such that these are the shape like this one, and it is again starts from this one, so this is a discontinuous, so this is not acceptable. Secondly, if the psi x is in this form, that means the derivative is not continuous. If you take the derivative of psi x with respect to x, it is not continuous, it stops here. So this is also not acceptable. And also, apart from that, if the psi x is in this form, then it is not single valued. So at this point, in this point of x, you can see there are two values of psi x. So this is also not acceptable. So these are the wave functions representations where which is not acceptable for psi x. Now this application of Schrödinger's equation, if you come to the applications of Schrödinger's equation, it is first used in a particle in one dimensional quantum particle, that is a nanowire, or you can also call it as a quantum wire. When there is one dimensional confinement, as the particle is moving in one dimension. That means from bulk if two of the dimensions are reduced to nanometer, then it forms a wire. So the particle, that is mainly the electron, is moving in this one dimension, and how the wave function will behave and how the wave function solution in terms of potential Schrödinger's equation can be found out. This is, so we call it as an infinite potential well. So we represent it as we assign here a certain dimension where the particle will be moving, and we associate a barrier of infinite energy surrounding it. So in this case, at this point u is equal to 0, there is no potential, but in these two regions, or let's say this goes to infinity, this u is going to infinity. So this represents a particle moving in one dimension potential. The Schrödinger's equations gets applied here, and the final solution is can be represented in this form. If we are considering only one dimension, then it is root 2 by L sine n pi x by L. This is a solution of this infinite potential. And so if we look into the energy distribution of this solution. So it will be discrete energy, right? So this corresponds to x is equal to 0, and this corresponds to x is equal to 1. So energy will be E1, n is equal to 1. Energy n will be n square h square divided by 8m L square. This is the expression of energy. So based upon that expression, we can have discrete energies, like for n is equal to 1, this is corresponds to E1, and the gap will increase as we go up. This corresponds to E2, that is N2, and so on and so forth. So the gap keeps on increasing. Now the wave function, if you again plot the wave function in the similar manner, for an infinite potential well, so this is x is equal to 0, x is equal to we're taking at 1, but because it has been normalized. So for n is equal to 1, the wave function will look like this. For n is equal to 2, that is psi 2, the wave function will look like this. For 3, it will be like this. So it keeps on increasing. And finally, the probability, that is the psi x square, is just there won't be anything below in the bottom region. So this corresponds to the first, n is equal to 1. This is for the second, and this is for the third. This is how it will look like.